Hi, I'm Ethan Katz-Bassett, and this is work with Harsha, who just spoke, and others at the University of Washington. So while with iPlane we've been analyzing the data for over a year now, we're just now beginning to mine that same data for reachability and black hole problems. So this is much more work in progress than the talk that Harsha just gave. So the most basic goal of BGP and the internet is to ensure global reachability. Basic idea is if there's a physical path, there should be a BGP path, and if there's a BGP path, then traffic should be reaching. But if you're like me and you regularly read the outages mailing list and NANOG mailing list, you know that that's not always the case, and sometimes it's hard to tell what's going on. Maybe some of the postings are Randy trying to get measurements for his experiments, but for instance, a couple weeks ago, someone was posting they'd lost a link from one of their providers, and they thought maybe the provider hadn't withdrawn the routes. They weren't really sure. They were asking for help figuring out what's going on. So these are the sorts of things that we're trying to look at. We started out by looking at some of the iPlane data and seeing how often we saw global reachability being violated. So on this graph, on the x-axis, we have the fraction of our vantages from which a prefix was unreachable. And it's a CDF, so on the y-axis we have the cumulative fraction of sets of probes, where a set of probes are the probes to a given prefix on a given day. So for instance, we see that on more than 70% of the sets of probes, we have perfect reachability, the zero unreachability, but it falls off pretty quickly from there. So if a prefix is unreachable from one vantage point, it's highly likely to be unreachable from many vantage points. And based on the knee of this curve, we're going to say that a prefix is experiencing reachability problems if more than 10% of the vantages fail to reach. So we saw, looking at 4 months of data, that on 85% of the days, between 10 and 15,000 distinct prefixes had problems. And over the course of our study, out of the 110,000 prefixes that we monitored, 79,000 of them had problems at least once. So we're seeing lots and lots of problems, most prefixes having problems at some time. So we're starting to design the Hubble system to try to address this. And the goal with Hubble is to come up with a system that in real time on a global internet scale can automatically monitor long-lasting reachability problems and automatically classify causes of those problems. So last year at NANOG there was a talk on modifications to BGP that could help address reachability issues during BGP convergence, short-lived reachability issues, and we're not really trying to address that. We're looking just at long-lasting chronic problems. In fact, currently we're just issuing probes every 15 minutes, so we're not even going to see short-lived problems in many cases. High-level view of our system, we're going to synthesize multiple information sources. So we're going to take BGP feeds, we're going to issue trace routes from distributed vantages, we're going to use interface alias information, and we're going to issue pings to check liveness and help monitor reachability of prefixes. And we're also going to keep around historical BGP and trace route data that will help us with our troubleshooting. So when we see a failed traceroute, the system asks a number of questions. First, where's the last hop that we see on the traceroute? If it didn't reach the actual destination, did it reach the prefix? If not, did it reach an origin AS for the prefix? Did it reach a provider for that origin? Or did it end somewhere further upstream in another AS? We can also ask, were other vantages able to reach the destination at that point in time? We can look at whether the origin was single or multi-homed. We can try to predict the next hop. So we can look for paths that reached historically through that same last hop that we just observed, or paths that are currently reaching from other vantages, and see if we can predict it. If we're able to predict where it should go next, we can check if that next hop is still live. We can also ask, is it in the origin AS? Where is it located? And then we can assess whether or not the path contains loops. So we've recently been done an evaluation of a real-time automated classification system. We probed 1,500 prefixes every 15 minutes for 2 weeks. And we observed over 100,000 problems, and we're able to automatically classify more than half of them as they occurred. And we're currently using a very simple classification approach, sort of trying to match common patterns that we observed. We're trying to find a common cause that can help explain a number of the failed trace routes to a prefix. And we're going to say, based on that earlier reachability slide that I gave, that a substantial number means 10% of our vantages. So it doesn't necessarily have to explain all of the failed trace routes that we saw. And actually, we can classify a given problem in multiple ways at the same time, either because we're observing multiple simultaneous problems, or maybe over the course of this 15-minute time period, someone was working on fixing the problem and the problem shifted away. We're also not necessarily pinpointing the exact problem. It could be downstream on the handoff from the last hop that we see, or it could be on the return path. And we're currently using 6 classes. So the first class that we're looking for, we're going to call the single-homed origin AS down. So here we have a prefix P that's our destination. It has an origin AS, and we're seeing a single provider A for that origin AS. And in this class, we have no probes successfully reaching the origin AS, but a number of probes are ending up in the provider. And this explained 31 of the problems that we saw. Sorry, 31% of the problems that we saw over the 2-week period, and at any given point in time, between 6 and 48%. The second class, now the origin AS has a second provider B, or maybe more than 2. And again, we're seeing no probes reach the origin AS, but probes are ending up in the providers. And this explained 13% of the problems that we saw. So the first 2 classes were both complete unreachability. And the next 4, starting with this one, are going to be partial reachability. So this is perhaps more interesting. Some probes are getting through. We know things are working some places, but not everywhere. And the first class we're going to call provider AS problems for a multi-homed origin. So here we have all probes that go to provider B are dying in provider B, but other probes are reaching through the other provider. And this explains 16% of the classified problems. And for us, this was one of the more surprising results. One of the main reasons for being multi-homed is to have resilience to failure. And in fact, we saw this really commonly where one provider wouldn't be getting traffic through. And sometimes these problems would last for days on end, where we'd continue to send probes that would end up in provider B and not reach, whereas other vantages were having no problem reaching the prefix. Next class is very similar. Here we have another ASC that's not a provider for the origin. It's somewhere upstream from B. All probes that enter C are failing, and we have some probes that are reaching other ways, either through A or perhaps through B. This explained 21% of the problems. So the first 4 classes that we looked at were all cases where the problems were sort of AS-wide. Any probes entering a particular AS were failing to reach the target. But as we saw in the Bogon filter talk earlier, it's not always sufficient to look at things on an AS level. Sometimes you have to look on a router level, and that's what those last 2 classes give. So here we have some AS that's upstream from the origin, and there's a router R in that AS. All paths through R are failing to reach the destination. We have some historical paths that reached through R, so we have some idea of where the paths should be going. And there are other paths through that same AS that R is in that are avoiding R and hence reaching the prefix. So this explains 6% of the problems that we saw. Our last class is very similar, but here we don't have historical paths that reach through R, so it's some sort of new path and it's not working. And this explained 26% of the problems that we saw. So to quickly summarize those results from our automatic classification over the 2-week period, about 45% of them fell into classes 1 and 2, which were the complete unreachability problems. And to highlight a couple of the interesting points on the partial reachability, we saw 16% falling into that class 3 where there's some problems going on with multi-homed failover. And then looking at class 5 and 6, we saw that when there were problems with a particular router not getting traffic to the destination, it was much more likely to be on a new path rather than one that had historically been working. So this analysis that I just gave was just on 1,500 prefixes, and we're now working to scale up this analysis to the entire internet, but we don't have to do trace routes to every prefix from every vantage point constantly. So we're going to do some intelligent target selection. We're going to maintain BGP information, and we're going to use pings to responsive prefixes to check reachability. We're going to then use these updates and pings to help us select prefixes that are likely to be experiencing problems at a given point in time. So either prefixes that are having lots of BGP changes, or if we see a failed ping. And from that earlier slide giving a graph on reachability analysis on the iPlane data, we saw that if one trace route failed to reach, it was likely that many vantages were having problems. So a single failed ping is likely to predict problems. This is ongoing work, and we plan to evaluate it this summer. So in conclusion, we saw lots of reachability problems, and although I didn't give very much data on duration in this talk, many of them are long-lasting. We also found that keeping around historical fine-grained data can help us with problem analysis. and we saw many more problems with multi-home failover than we expected. In the future, we're going to deploy that hybrid probing approach that I talked about to scale this up to internet scale. We're going to work on predicting the availability of paths and prefixes from our historical data, and we're going to develop a query language interface to make this data available. We'd really like to build a system that's useful to you and that gets used, so we'd really like to know what we can do to help you. We'd like to give access both to the actual traceouts and to our reachability analysis. And we'd love for you to let us know other problems or causes we should look for. Is the system headed in the right direction? Should we change it in certain ways? Please email me. It's ethan@cs.washington.edu. And in the future, we're hoping that you can help us refine our techniques by verifying specific problems that we've seen. Thank you. Happy to take questions.
We've got time for a couple questions, if you want.
Randy Bush, IJ. Back one slide. The reachability problems that were non-long lasting.
Yes.
And might be associated with multi-home failover. Could you do an analysis to show the length of time that they weren't long-lasting and correlate with BGP data for those of us who are trying to stop route flap damping?
Yes, it's definitely the type of analysis we can do. I haven't looked at it specifically for multi-home failover, but we did do some analysis of how BGP updates correlated with outages.
And?
I'm sorry, what?
And?
Well, so we found that that BGP was only sufficient to explain a third of the problems we saw, but that
a third of the short terms, or you're counting?
I don't think we did the analysis on over time.
Thank you.
But we'll do it.
Are there any more questions for Ethan? Okay, Ethan, can you mail the current set of those slides to the PC? Can you mail the current set of that deck? I think the one we have online is a little older.
Okay, sure.
Appreciate it, guys. Thank you.